Good day, students. In this clip, we're going to be going over part 2 of the 1969 AP Calculus AB multiple choice exam. We're going to be doing questions 6 to 10 in this series. Okay. All right, let's take a look at question number 6. It says, what is the limit as h approaches 0 of 8 times 1 half plus h to the 8 minus 8 times 1 half to the 8 over h. Okay, so let's take a look at this. What does this look like? Well, if you think about the first lesson on derivatives, what was the definition of the derivative of a function? If you have a function f of x, the derivative f prime of this function is a limit as h approaches 0 of f of let me color code it for you to see, f of x plus h, okay, minus f of x divided, and then this whole thing divided by h. Okay, so this is a definition of the derivative of a function at x over h. All right, so let's see if I can express this limit as a derivative. I can evaluate this limit by evaluating the derivative of the specific point. So how do I identify the function here and then find the limit, find the derivative consequently? Let's see. So I'm going to rewrite the function down here. We had limit as h approaches 0 of 8 times 1 half plus h to the 8 minus, I forgot already. Let's see what it is. 8 times 1 half to the 8th power. And this whole thing divided by h. All right. So what we can do here, so let's divide this over h. Now let's compare this limit we have right here to the definition of a derivative up here. Okay. Now the easiest way to identify it is if you focus on the term after the minus. That's the easiest way to find out what the function is. This is f of x right here. This is f of x, this whole piece. So this function right here, this piece of this limit can help us identify what f of x is. So the argument of the function in this definition is x. Hence the input right here is 1 half. So guess what? X equals 1 half. All right, x equals 1 half. All right. So what this is in essence is basically this is basically f prime of x when x equals 1 half. Or you can write this as simply put f prime of 1 half. Okay? So the question is, what is f of x so we can differentiate it and evaluate it at 1 half? Well, we just simply replace this 1 half with x. So we're going to have f of x equals 8. I'm going to take out the 1 half and replace it with x to the 8. So there goes the function. All right? So now that we have f of x, we just need to find the derivative of this function when x is 1 half, because that's the input here, that's the x, and that's the x right here. All right, so let's find the, I'm going to do it step by step. I'll find the derivative first, and then I'll evaluate it at x equals 1 half. All right, let's use the power rule. F prime of x is going to be 8 times, this 8 goes to the front, and then x to the minus 1 from the 8, 8 minus 1 is 7. Okay, so that's going to give us 64x to the 7th power. All right, so now that we have the derivative, we're going to evaluate it at x equals 1 half. All right, so what we're actually looking for is f prime of 1 half. So f prime of 1 half is basically what you get when you evaluate this output at x equals 1 half. Okay, so 64 times 1 half raised to the 7th power. Okay, 64 times 1 half raised to the 7th power. All right, now so let's close that out to the 7th. All right, so 1 half to the 7th is basically multiply this. We have just use the power property of exponents, and then we're gonna have 1 to the 7th over 2 to the 7th, which is basically 64 times 1 over 2 to the 7th is 128 over 1. 64 goes here once, 64 goes here twice. So our final answer is 1/2. All right, which is option B. So let's go up. Option B is 1/2. Okay, so there you have it. It's just basically an application of the definition of the limit definition of a derivative. All right, let's take a look at question number 7. It says, for what value of k will x plus k over x have a relative max at x equals -2? So obviously we have a relative max at this value right here, but what x value will make that happen out of this four options? All right, so whenever we're looking for an extrema, we know what happens when you have an extrema. If you have an extrema or max or min, um, the first derivative, f of c is equal to 0 when there is an extrema, extrema is a max or min, okay? Extrema at x equals c. In this case, the extrema is -2, and the nature of the extrema is a maximum, all right? So if we set the derivative of this function to 0 and solve for k, inputting the value of our extrema, then that will tell us the value of k that will make this true, all right? So the function under consideration is f of x equals x plus k over x. The plan of attack is to set the first derivative equal to 0, which will help us find the extrema. Plug in the value of our extrema into the function, and then we'll find the value of k. All right, so let's do it. So I want to find the derivative of this function first, but I don't like how this component right here looks like. It has the x in the denominator. So this would be a good case where we can rewrite so that it makes it easier for us to find the derivative. All right, so I'll rewrite this as f of x equals x plus, using the law of exponents, xk to the -1. All right. Okay, now we can find the derivative using the power rule with ease. So f prime of x equals derivative of x is 1 plus, using the power rule here, if you differentiate that, you have times -1. Or I should have factored out the k because that's a constant. Take out a k times -1, x to the, subtract 1 from that, -2. All right, let's simplify that. F prime of x equals 1 minus times plus minus kx to the -2. All right. Okay. Now, when do we have a maximum or a minimum? We have an extrema when the derivative is equal to 0. So what I'll do is I'll set the derivative to 0. 1 minus kx to the -2 equals 0. All right. So the value of the extrema, the value of the extrema was -2. So I'm going to plug in -2 into this function and solve for k. That will tell me the value of k that guarantees a maximum there. All right. So before I do that, let me rewrite this as 1 minus k over x squared equals 0. All right. So we know that f prime of 2, -2, equals 0 will give us the maximum. Okay, so what k value will guarantee that this happens? Let me verify it's -2. Yeah, good. All right, so let's plug it in. So we're gonna have 1 minus k. So the value that gives us a maximum is -2. -2 squared equals 0. So let's solve this for k and see what k value it is. Okay, so we're gonna have 1 minus k over 4 equals 0. And then we can write this as k over 4. Just add k over 4 to both sides. You have k over 4 equals k over 4 equals 1. And then you multiply both sides by 4. And you have k equals 4. Okay? So this is a value that guarantees there to be a maximum at x equals 2. So the answer is option D. All right. All right, let's take a look at question number 8. It says if p of x equals x plus 2 times x plus k, and if the remainder is 12, when p of x is divided by x minus 1, then k equals what? This is an excellent example of the application of the remainder theorem, okay? The remainder theorem. So think back to pre-calc. What does the remainder theorem tell us about how to find the remainder after you divide a function by a binomial? Uh, so let's say we have, so if px is divided by, let's say, binomial x minus r, then the remainder is simply p of r. Okay, you can use long division or synthetic division to divide and find what the remainder is. But the quickest way is just simply find the root and then plug it into the original function. Okay, remember you always have to take the opposite. Okay, you basically solve x plus x minus r equal to 0, and then whatever result you get, you plug it into the function, and that will be the process that will generate the remainder. All right, so we have the function here, p of x equals x plus 2 times x minus k, x plus k. So to find the remainder using the remainder theorem, we just simply plug in uh, the root of x minus 1, or the opposite of x minus 1. That's what I'll plug in here. So you have to be really careful here. Some people will just plug in -1 and you get a wrong answer. You have to go x minus 1 equals 0, and you actually have to solve it. All right? If you solve this, you get x equals 1. So you plug in the opposite. All right? So be careful with that. So what we're evaluating to find the remainder after dividing by x minus 1 is p of 1, okay, which is what you get when you input 1 into the function. So 1 plus 2 times 1 plus k. Okay, now we also know that the remainder is 12. So I'm just going to set this equal to 12 because this equation is equation for the remainder. So I'm going to have 1 plus 2. Let's just evaluate while we're at it. 1 plus 2, which is 3, times 1 plus k. We set that equal to 12. All right. All right, so let's solve this. This is going to be 3 plus 3k equals 12. We subtract 3 from both sides. We have 3k equals 9. Divide by 3, k equals 3. All right, so this is the value that will make the division. When we divide this function by x minus 1, when k is 3, that will give us a remainder of 12. All right, so the answer is option letter B. Okay, so there you have it. All right, let's take a look at question number 9. It says, when the area in square units of an expanding circle is increasing twice as fast as its radius, in linear units, the radius is. So basically, we know that there's a relationship between the change in area and the radius. If a circle is expanding, so at a point in time, at a particular point in time in that expansion, the area is going to be growing twice as fast as the radius. So what is the radius at that point in time? This is a typical related rates problem. So when we're working with related rates, what we need is basically a formula that relates to measures that are changing, and then we'll differentiate them implicitly, plug in what we know, and then we can look for the missing component, okay? So we're dealing with area of a circle right here. So what is the formula that relates the area of a circle and the radius? It's your typical area formula in geometry, right? So we know that area is equal to pi r squared. All right, so if there's changes going on here, how are they related? So we just need to find the derivative of this function implicitly. We're going to differentiate everything with respect to time. So we're going to differentiate the left side. This is going to be dA dt equals, and then on the right side, this is a constant, so we can factor that out. Differentiate this. It's going to be 2r dr dt. Okay, so there you have it. This is the formula that relates the change in area with the change in radius. So let's make this look nicer. dA dt equals 2 pi r dr dt. Okay? All right, so now that we have this related rates equation, let's go back to the problem. It says that when the area is expanding twice as fast as the radius, so basically the change in area is the dt, and the change in the radius is the rdt. Okay? So at a point in time, the growth of the area was twice the radius. Okay? So what does that tell me? That basically tells me that the ADT is equal to twice 2 the RDT. Okay? So this is at a particular point in time, this is what was happening. So what is the radius at this point in time? So what I'm going to do is I'm going to use this fact. I'm going to substitute this fact into my equation, and then I will solve for r. Okay, let's go ahead and do that. We're going to have, I'm going to replace the ADT with 2 the RDT, because at that point in time the ADT was going twice as fast as the RDT. That equals 2 pi r the RDT. Okay. All right, so I can divide both sides by the RDT. So divide left, and how about 2 the RDT? We can do that. So divide by 2 the RDT, because I see that they're common on both sides, 2 the RDT. All right, on the left side, that divides out to just 1. 1 equals pi r. Okay. All right, so to finish this up, we just need to solve for r. So to get r by itself, divide both sides by pi. Divide the left and the right by pi. And then the radius, when the area was going twice as fast as the radius, was equal to 1 over pi. Okay? So it's just a good application of related rates. So the answer is 1 over pi. All right, so that is and the answer is option letter C. All right, let's move on to the next question, question number 10. It says a set of all points e of t, e to the t, comma t, where t is a real number, is a graph of y equals what? This is like a parametric equation. So we have the input and the output there. So let's see, we have, remember for any coordinate system, what we have is two variables, is x and y, right? X and y. So in this case, we have e to the t and t. Okay, what does this tell me? It tells me that x equals e to the t as the first coordinate, relative coordinate, and y equals t. Okay, we can make a substitution here. Since y is t, how about I substitute y for t in this equation, in the first equation, so I can have an equation that relates to 2, and see if we can isolate y. Okay, so substitute y for t, and x equals e to the t. So what does that look like? We have x equals e to the y. Okay, so now if I can solve this equation explicitly for y, that will be the result I need. All right, so remember the inverse of exponentiation. The inverse of e is a natural logarithm. Okay, so to nullify this, I'm going to take the natural logarithm of both sides. Okay, so natural logarithm of x equals the natural logarithm of e to the y. Okay, all right, so this is going to become natural logarithm of x equals, remember ln of e is just 1, right? So I can write this as y ln e. So it's going to be natural logarithm of x equals y times 1, which is just y. So y equals the natural logarithm of x is the function that guarantees that the output is going to be real numbers. Okay, so y equals ln x, where t is a real number. That's where you have this condition satisfied. So our answer is going to be option letter E. All right. Well, thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And you can click like if you like this clip. And please, please, please post a comment to let me know what you think about this presentation. More clips can be found on myclipserve.com. Thanks again, and have a wonderful day.